Hello from Germany. I think we can start now. So welcome to our webinar. I am very happy how many participants are online with us today. My name is Victoria and I am your host today. So before we start, just a few remarks for your information. Please feel free to type in any questions that come up during the webinar in our question box. And then we will answer as many questions as possible at the end of the webinar. If there are too many questions, please don't worry. We will answer each question via email within the next days. And if there are any technical problems, please don't worry too. This webinar is being recorded for you. You will automatically receive a recording of the webinar within the next 2 days by email. Well, and now I would like to introduce you to our today's speaker, Dr. Elena Moukhina. Elena studied physics and mathematics at the Yaroslav State University and has a PhD in physics. She has been part of NETZSCH Analyzing and Testing family for over 20 years now and has gained lots of experience in our R&D department before taking over the position of the business field manager for the software Kineitcs Neo last year. Elena has been a huge contribution to the development of the Kineitics Neo software, which she will demonstrate here today. So welcome, Elena. We are very happy to have you here today talking about kinetics for polymers. I will now hand over to you to get started. So enjoy our webinar and have fun.
So, hello everybody. Hi everybody. I think you hear me. And now we speak about kinetics for polymers, decomposition, curing and crystallization by Kineitcs Neo software. Here will be two parts. First is introduction, what kind of problems could be solved, what the idea, a little bit theoretical background for this, and then applications. Applications of three types for our polymers: decomposition, curing, cross-linking, and crystallization. Let's start. First, why we need kinetic? Because sometimes we would like to ask the questions which we cannot answer by other means. For example, we could ask about lifetime predictions or some other things. So we should know something about reaction mechanism, and we would like to predict material behavior at the conditions where it is impossible to measure. And we can measure maybe several hours or several days, and sometimes we must know right now what happens with this material in several years. And then we can just make a few short measurements in our laboratory, and after that use our software, make kinetic analysis and make predictions for several years. For example, here, sometimes we have some wire insulation from polymers, and this wire insulation has some lifetime, and this lifetime depends on the temperature. And after this lifetime, there is some kind of degradation of this polymer, and material is not elastic anymore. It could be broken, and you know that if electrical insulation is broken, it's very dangerous. And therefore, we must know before we use this material how often how frequent this material should be exchanged. Should it be exchanged in 5 days, in 5 months, in 5 years? And for example, for electrical insulation, it's important because it works not always for room temperature. It works, for example, in some electrical equipments inside the electrical engines, and there is enhanced temperature inside, and therefore lifetime could be much shorter. Another situation is, for example, for coating of pipelines. So before we use this material, we must know what is the lifetime of this coating. Is it 5 years? And in 5 years, it should be exchanged, or maybe in 20, maybe in 50 years. Another one is curing and cross-linking. Here, here we would like to know how the process goes on, where is the glass transition temperature, what is the degree of curing in the final state, are we in the glassy state or in liquid state or maybe in elastic state, and Kinetic software can help you to answer this question. Here is a new part, is a firing of ceramics. And you know that ceramics, during the production of ceramic, there is a debinding of polymer happens. And usually the quality of ceramics very high sensitive to the temperature, to the heating rate to the temperature profile of firing. If heating is too fast, then decomposition of polymer is too fast, and then gas production is too intensive, and therefore it would be damage in the structure of ceramics. If you make too slow, yes, the quality is good, but for high temperatures, you know, it is really too expensive. And the question is just to find the optimal profile for firing of ceramics. Another kinetic problem is crystallization. For example, for thermoplasts, for PET, for the plastic bottle. And if it works, production happens at the correct temperature, then this plastic bottle is transparent. If during production something wrong with the temperature, then this plastic bottle could be not very transparent and it is optically not so nice. So the question, how to create the desired property of material during its crystallization. Now, how it works. Firstly, we take our material, go to laboratory, make some measurement of the same process at different temperature conditions, at different heating rates, for example. You see here are different curves because they are measured at different heating rates. After that, we create kinetic model because here the curves are different because temperature is different. But what is the same? Chemistry is the same. It is the same activation energy. It is the same order of reaction. It is chemically the same reactant and the same product. And we can put this information, which is the same for all curves, into our kinetic model. And if we know this information, then this kinetic model can describe our process for any time and for any temperature, for any heating rate. Let's see if this one model has, if the calculation which are done for this model is in agreement with experiment everywhere for all curves, then this model is correct. And it means that this model can be used for predictions at any temperature and at any temperature profile, any heating rate. And now we can use this model for simulation. We can simulate TSC, we can simulate degree of curing, degree of crystallization for any temperature profile, for isothermal temperatures or for complex temperature profile. How it works inside. Firstly, we must have some measurements which reflect the information, which contain information about process. For example, for decomposition, we can use a thermogravimetry because during decomposition, the mass of material decreases. We take the balance, thermobalance, put here a sample, make heating and see what happens. Mass at the beginning is higher, at the end, after decomposition, it is lower. And here is some kind of decomposition happens. We can make a same for different heating rate, fast heating or slow heating, and we see that everywhere initial and final mass is the same, but in the middle it is different because this process is time dependent. And for different heating rates, it will be different. Here we have a curing For curing, the mass is the same, but we know that during curing, reaction is exothermal and some heat production happens here. So we can measure this heat energy which happens during chemical reaction. For this case, we can use differential scanning calorimetry. We have the instrument with two crucibles. We put sample, make heating, and measure a heat flow. And if there is some production of the heat, then DSC curve has a peak. During the heating, we can make fast or slow heating, and then we have some peaks. If heating is fast, then reaction is very intensive and the peak is higher. For slow heating, reaction is not so intensive and therefore peak is not so high. Here, here are thermoplasts. And for thermoplasts, during crystallization, we know again that some heat energy is produced. We can use again differential scanning calorimetry, but in this case, we make cooling from high temperature to low temperature, from liquid state to solid state. And again, we can measure heat flow, we can make a heat which produced during crystallization. We can make cooling fast or slow. Then we have different curves, and these curves can be used for our kinetic analysis. Another one is areometry. Sometimes it is necessary to know how viscosity changed. And if we have some material, in this case, we can measure it with a areometer. We put our material into areometer, for example, here rotational areometer, make heating. And if nothing happens, no any chemical reaction happens inside material, then we have decreasing curve. For low temperature, here viscosity is high and material, you see, it's more solid. And for high temperature, material is more liquid and viscosity is much less, is very low. And if we have some chemical reactions, for example, for adhesives, for paints, for epoxy, then the viscosity curve looks like this. Here decreasing for a reactant, here decreasing for product, and here increasing behavior during our reaction. We can make it fast or slow, and then we see that a result depends on heating rate. Now we have totally different measurements techniques, and we should come to some value which describe only chemical things, which is independent on technique. In this case, there is some value which called degree of conversion, or alpha, and it shows what part of a reaction is already done. For example, for thermogravimetry, we have reactant, we have product, mass of product, and measurement during decomposition has some step. And if we make a ratio between current mass loss to total mass loss, then the value called alpha, it is degree of conversion. It is changed from 0 to 1. 0 means reaction is still not started. 1 means reaction is already finished somewhere here. And here, for example, a half of reaction is already done. Here is maybe 20%, here is 80%. So degree of conversion shows what part of reaction is already finished. If we speak about DSC, then again, we make a ratio between the current area until the current point to the total area of the peak. And then again, we have a value from 0 to 1. 0 reaction is still not started, 1 it is already finished. Viscosity, we have behavior of reactant, we have behavior of product, and if we have a curing reaction, then there is a step in our measurement, and there is, if we make calculation of a change in viscosity, in current viscosity to the total viscosity at this standpoint, then again we have a value of conversion which is changed from 0 to 1. So it doesn't matter what is the original signal. Is it DSC or TG or viscosity? For each case, we recalculate measured data to degree of conversion. And now how it works really with the software. Firstly, we go to laboratory, make measurements. It doesn't matter what kind of instrument. It could be DSC, TG, depending on your process. Then we put this data into the software. We make some processing. We remove baseline. We recalculate everything to degree of conversion and have several curves, which shows only a real chemistry or maybe crystallization of our process. After that, we apply kinetic methods. It could be either conventional method or so-called model-free methods. For example, Friedman, Azawa, Kissinger, or it could be modeling for autocatalytic reactions and autoreaction Kamal Sorrow. During this application of kinetic method or kinetic modeling, we have finally one model or one mathematical model, we can say, which can describe all experimental curves. So for 4 curves, we have not 4 models, but only one model. And this model has temperature and time as a parameter, and all other things like activation energy or order of reaction are the kinetic parameters. They are inside the model. And if this model works for different heating rate for our experimental curves, then we can use this model for predictions for any temperature conditions, for isothermal, for dynamic, with heating, for arbitrary temperature conditions. We can predict different type of signal. We can predict degree of cure, curing rate, or maybe crystallization rate, degree of crystallinity, viscosity. We can make optimization of temperature profile for constant conversion rate or for given curing profile. What is inside? Let's go to the energy of our reactant and product. If a reactant molecule of reactant want to react and go to product, then this molecule could goes energetically to the over transition state and must overspring it, and the height is value is activation energy. So this reactant must have additional energy of activation energy in order to react. And this was described by Arrhenius equation. And here we have activation energy, pre-exponential factor, and type of reaction. For example, nth order reaction or autocatalysis, maybe nucleation for crystallization process. There are several approaches to solve this equation. The first, the easiest one, is model-free or isoconversional method, and another one is model-based. The first is model-free. Make assumption that there is only a reactant and product and no any intermediate products between them. So it's only one step, we can say, and here is only one kinetic equation, and all complexity of this process is described by dependence on alpha, for example, activation energy. At the beginning of the process has one value and at the end of the process has another value. And the same with pre-exponential factor. And here for model free, it is assumed that the total effect is the same for all curves. And here, and another type is model-based. For model-based, it is assumed that the complex process contains of several individual steps. For example, A goes to B, B goes to C. And we have the number of kinetic equations is equal to the number of steps. For each step has own equation. A goes to B has the first equation, B goes to C has another equation. If there are 20 individual steps, then there is 20 kinetic equations. And each individual step has their own activation energy, has their own pre-exponential factor, and has their own reaction type. For example, the first one could be nth order and the second could be without the catalysis. It doesn't matter. Here it is assumed that the total signal is a sum of individual reaction steps. And now let's go more in details. Firstly, for model-free methods, there are two groups. The first is one-point methods. Here only a maximum point is taken for each curve, and then these points are shown in Arrhenius plot. Here horizontally is 1 divided by temperature. It's Arrhenius axis, and vertically logarithm of heating rate, and then all these points are on the straight line, and the slope of this line is proportional to activation energy. So we take maximum points, put them here, and find one value. Result is only one value of activation energy. Good that it's very easy, bad that here some additional things is not taken into account. Only one point is taken into account. So for complex reaction, we can forget these methods. Another are multi-point isoconversional methods, multi-point model-free methods. For example, Azawa, Kissinger, Kahira, Sonoza, Friedman, Vizovkin, etc. Here, the points, not only one point, but several points are taken into account. For example, the point with one value of activation energy, here is 50%. Then we have some points from different curves. On Arrhenius plot, it is one line with a slope, and from slope activation energy for this conversion could be found. Then the same could be done for another value of conversion, for example, for 80% conversion. Then there is another line, another slope, and another value of activation energy. So it means that the activation energy is different for any conversion. This could be done for any conversion value, and result of this analysis is a function, activation energy as a function of conversion. What's good? Again, it's fast. What bad? That for each point, only one value of activation energy is found. But if you have some parallel processes, independent processes, competitive processes, then you have only one value. But if you have some mixture with independent reactions, this value is not the first, is not the second process, it's just some intermediate value, and it could be some problem with analysis of really complex things by model-free methods. Here, another approach is model-based. If you have two steps, then it is assumed by model-based method that we have two individual steps. A goes to B, B goes to C. Reactant goes to intermediate reactant, has the own value of activation energy. And then intermediate reactant goes to final product. There is another value of activation energy. And finally, we can just put this model or just select this model in the software, and the software said that the first reaction, here is reaction rate, conversion rate. The first reaction has one step here, and it goes slow to the zero. A second peak is something like this here. The final reaction is a total signal is a sum of these two peaks, and somewhere here we have parallel two reactions which go parallel. Here for model-based we can make analysis for peaks with the same direction, like here, for example, step number 1, step number 2. Here we can see each step individually, and as some of these peaks, we can see a concentration of each reactant, concentration of initial reactant, then concentration of intermediate reactant, and then the concentration of the final product here. And if you have 20 steps, then you can see concentration of each reactant individually. So this is advantage of this method. Additionally, this method can make analysis for the process which have peaks of different directions. For example, endothermal and exothermal together. It happens really very frequent, and sometimes for TG, you can imagine you have a mixture of two components. One has decomposition with mass loss, and another has at the same temperature oxidation with mass gain. And then you have a process of different directions, and you can analyze them only by model-based method. And in this case, you have step number 1, step number 2, and a final curve is a sum of the steps. And again, there is a possibility to see the concentration of each product, including intermediate products. Now we can compare both these approaches, model-free and model-based. Model-free is really very fast. It's only one click, but it has a lot of disadvantages. It doesn't work for mixtures, for competitive steps. It doesn't work for Kamal-Soror reactions. It is curing for Kamal-Soror reactions because there are some parallel process happens. Reactions with diffusion control for crystallization. Steps of different direction, highly overlapping steps, mechanism where peak area changing with the heating rate, and there is no any information about intermediate steps. For model-based, everything works, but here you must have some elementary chemical knowledge about the process. And there are some rules how to create this model, and I'm really highly recommend you to read the paper ICTAC kinetic recommendation. And here there is information. ICTAC is International Confederation of Thermal Analysis and Calorimetry, and they write the rules how exactly this model-based analysis should be done and how exactly you should select your model during kinetic analysis. Here now applications. We have decomposition, curing, cross-linking, and crystallization. For decomposition, firstly, is lifetime. For example, we have the same coating somewhere in Norway, somewhere on the Orient, and you know that it will be not the same lifetime. Sometimes our customers work with some coating for big constructions. For example, for bridges, it's necessary to know how often it should be replaced, each 5 years or each 20 years. And we can speak, of course, about the cables. And the next one is ecological problems, and we should know everything about degradation of plastic waste, how to work. For Arrhenius equation for degradation or decomposition, the type of reaction is usually nth order reaction, and here the n for solid, for decomposition of solid, is not always integer. For example, for 2-dimensional or 3-dimensional force boundary reactions, value of n is not integer. How it works? We go to laboratory, make measurement, have 2 steps, make the modeling. Yeah, you see that points are our experimental data from 0.1 K per minute to 1 K to 10 K per minute, and lines are fit, and they here have a good agreement. All measurements are about 100 hours, and now we would like to make predictions for several years. We go to our software, select type of predictions is climatic predictions. Here we have information about more than 100 real weather stations, and each weather station has real historical data over 30 years for day and night during these 30 years. And now we can select a station. We can use historical data for 30 years, or there is a possibility to use, for example, for historical data for 1 year only because of global heating. And then we can make predictions for 10 years and see here we have temperature and how mass will be decreased during these predictions. Here we take into account only decomposition because of temperature. We do not take into account sunlight. So if your material is on the sunlight, then the light has also additional effect and decomposition could be faster. But if it's without direct sunlight, then we have real predictions. Here is sintering of ceramics. For ceramics, it is result is very sensitive to the firing temperature profile and the question how to improve the quality of product and reduce the production time. During firing of ceramics, there are two processes. One is below 700 degrees C, it's debinding, it's decomposition of polymer, and another above 700 degrees C is densification, and it could be measured by dilatometer. Now we will speak only about the first part because our topic is polymers. Debinding and decomposition of polymer, they could be measured. This decomposition with thermobalance, we have measurements, we have kinetic model for this measurement, and now we can make optimization. How it works. Here are the original non-optimized temperature profile, and here we have a debinding or decomposition of polymer for non-optimized temperature profile. It is relatively long. If we calculate the first derivative, then we see that there are some spikes, and these spikes means a too intensive decomposition of polymer, and exactly at this point there could be decreasing of the quality of our material. And now we can make optimization. We can reduce this spike, and we can make as short as possible. After optimization, we have a new temperature profile, and we have a new mass loss or debinding range. And here the real optimized profile is much shorter, and the higher value of the spikes is less than original. So we have improved quality, and we have reduced the firing time. Here is example, one of our customers, here is firma Haldenwanger from more advanced material. They produce a new ceramics, which is ceramic foam. And for this ceramic foam, that was really very problematic to find a new firing temperature profile. They come to us and ask us to optimize their profile, and we have reduced the temperature, the time for firing more than 50%. They were really happy. Another situation is cross-linking. Here we can speak about, here we usually use DSC data. For curing, we have materials like paints, like adhesives, like epoxy, and we would like to know how fast this reaction happens. During curing, it is the same Arrhenius equation, but for reactions of curing, the reaction type is autocatalytical type, and usually the Kamal-Surur equation is used for curing. This reaction has two parts where a reactant goes to product by two different ways. First one is nth order reaction, and a second one is autocatalytical reaction. And this type of reaction is inside our software, you can use it. Another one is, here each pathway has their own value of activation energy. Simplified version of this reaction is CMN. Here it is a same two different pathways, but the activation energy is same for both of them, and all other is the same. One is nth order reaction and another is autocatalytical. And the last one is pure autocatalytical reaction. There is only autocatalytical part. Here is example: phenylglycidyl ester with aniline. We have measurement with different heating rates, and we have model of CN type, and there is perfect fit, and it means that this model can be used for predictions. Another one here is epoxy. For epoxy, there is two different peaks of different direction. First is endothermal, another is exothermal. You can create two steps, and then after fitting, we have a good two-step model which can describe both steps, and then this model can be used for predictions. Here is phenol formaldehyde resin with glass transition and really complex peak, and we can make measurement at different heating rate from 2 to 5K per minute. Then the model is done. This model can be used for predictions for any temperature profile. Here we have temperature profile with two isotherms, and we can see how what is degree of curing for this resin. Here is very interesting UV curing. For UV curing, we use our photo DSC, where material is exposed by ultraviolet light. And there are two different types of UV curing. One is cationic, for example, for epoxy, and another is free radical for example, for acrylates. And here we have experience with both systems, and with Kinetics software, we can find a model and then see how long reaction with light should go in order to have your teeth really hard with necessary value of curing, or for your nails, or maybe for ink printing or for 3D printing. Here another is diffusion control. Here polymer has two states. One is glassy and another is rubbery. Between them is glass transition temperature, and for material is glassy state, there is slow curing. In rubbery state, it's a fast curing because material is very elastic. A problem is that during curing, glass transition is not on the same position. It changed from low value to high value. Therefore, during our modeling, we must firstly find what is the glass transition, and if our material below or above glass transition, and if our reaction is slow or fast. Firstly, it is necessary to find glass transition dependence on conversion. 0 here is conversion, 0 reaction is uncured, 1 is reaction totally cured. Here is a temperature for uncured state and for cured state, and there are a couple of points, intermediate points, which should be measured additionally. Then we use Di Benedetto approach to find dependence, how glass transition depend on conversion, and then we can use it for predictions. How to measure glass transition, how to measure this intermediate point? Firstly, we make heating and with partial curing, not until the end. Glass transition temperature is the temperature for uncured material, then make cooling and heating again. The next glass transition here is higher than the first one because the material is partially cured and glass transition temperature is moved. From rest curing, we can find a value of alpha which correspond to this partially cured glass transition. Here is example. We have different heating rates from 0.5 to 5K per minute. We can recalculate everything to degree of conversion from 0 to 1, and we see that everywhere reaction goes fast until some point, and after this point reaction goes slow, and for 5K per minute reaction goes fast almost until end. For 0.5 or for 0.2K per minute this changing happens very early, and this point where mechanism is changed is the point where sample temperature crossing glass transition temperature, and here we have a vitrification point. Material changed its state from elastic state to glassy state, and then curing is very slow. And now for this situation, there is for this model, sorry, I just show that in the software you can just click diffusion control, and then this model could be done with taken into account glass transition. How it works? Here, for example, with our software, there is a possibility to make a simulation not only for signal or degree of curing. We can predict how glass transition changed during the curing for your temperature profile, and additionally we can calculate, software can calculate some temperature transition diagram. What is it? Here let's speak about isothermal conditions. Here is a temperature of a sample with a time, and the temperature of glass transition temperature of polymer at the beginning is somewhere below current temperature, and at the end is above current temperature, and somewhere there is a crossing of it. The first period we are above glass transition, we have fast curing, material is elastic or liquid, viscous liquid, and after this point we are in glassy state and the curing is very slow, and this point is vitrification point. We can find vitrification point for another temperatures, for example here for 150 or for 30 degrees C, and a black curve is our vitrification curve, which shows a point where material changed its property to glassy state. Here is time temperature transition diagram. After glassy state material is after vitrification line material is glassy, and before it could be either viscous or rubber depending on gelation line. Next point is a curing for a real logical data. Here we have our rotational remeter. We have some measurement with different heating rate from 0.5 to 5K per minute. We have a same initial and final data, but we have a different values in the middle because process is time dependent. Now we can load this data into the software. Here is from our customer who allow to show this data. In software, we select tangential baseline, select a range for evaluation. Then the software will calculate baseline for reactant, baseline for the product, and remove it. Here, measured data, then prepared for analysis, where baseline is removed. And here is kinetic model, where modeling is done. Points are experimental data, and lines is our model, which can be used for predictions. Now for predictions, we can put any temperature profile and use this model in order to see how a reaction goes on. Here is a temperature, And here is degree of conversion, which is at the beginning null, 0, at the end is 1, and here some curing happens. But sometimes for a real simulation, especially for our automotive customers, and they ask to know not only degree of conversion, but a real value of viscosity. Because if a real absolute value of viscosity is not taken into account, then there could be some problems with drops, orange skin, and here some non-uniform curing. And now in the software, we have a possibility to make predictions of absolute value of viscosity for any temperature profile. Here, viscosity goes down because of reactant, then goes up because of curing, and then goes up again because the dependence for product on the temperature. Here is crystallization. For crystallization, there is isothermal crystallization or non-isothermal crystallization. For example, here we have isothermal crystallization for polyamide 12. We have different isothermal conditions. Then we can recalculate it to conversion and apply Avrami nucleation, where alpha, degree of conversion, is 1 minus exponent, here exponentially goes, from constant and time power to n, where n is dimension of nucleation. K is the value of which is different for temperature. It's a decreasing function. This decreasing function could be different. Here, f of alpha, either Avrami or Shostak-Berlin for crystallization, and the k is a function of temperature, could be either Arrhenius or non-Arrhenius. And this is for model-based, and for model-free, it is only Arrhenius approach. Here, inside the software, we have all 4 combinations for crystallization. It is Avrami plus Arrhenius, Shostak-Berlin plus Arrhenius. They both work only for isothermal crystallization. Then Avrami plus Hofmann-Lauritsen is Nakamura. Shostak-Berlin plus Hofmann-Lauritsen is Sbertsoli model. They work for both isothermal and cooling crystallization. And of course, we have some model-free methods, which works only for Arrhenius approach and only for isothermal crystallization. And here we apply for polyamide Arrhenius approach with Shostak-Berlin reaction type, very good fit, and we can use this model for simulation, for example, for simulation of degree of crystallinity for other temperatures. But again, Arrhenius approach, which works only for isothermal crystallization and only for isothermal predictions. Advantage of Arrhenius approach: very fast, but it has no physical background. The activation energy is just the apparent value, and it is negative. It has no any physical sense. This method doesn't work near glass transition and works only near melting point. If we make heating and cooling, then we have a glass transition and melting. And the Arrhenius approach, which was shown right now, works only here for isothermal crystallization. But if we have a real cooling, then crystallization happens here, and it is outside of Arrhenius approach. Therefore, we should use here non-Arrhenius approach. It is Hofmann-Lauritsen approach, which works from temperature T infinity, which is a little bit below glass transition, until melting temperature. Again, for crystallization, we have Arrhenius approach and non-Arrhenius approach with Hofmann-Lauritsen theory. This non-Arrhenius approach has 2 terms. A first is diffusion, works near T infinity, near glass transition. It is described how crystallization goes near in the glass transition range. A second one is nucleation term, and it works in the range of melting and depends on supercooling. Here is supercooling is the difference between melting temperature and the current temperature. This method works between glass transition and melting. Example is PBT. Here we have different cooling measurements with different cooling rate. We apply Sviatozzoli model for Hofmann-Lorentz theory and Shostak-Berggren for reaction type, and we have very good fit, and we can use it for crystallization, just for simulation. And let's see, for slow simulation, crystallization is complete. It's cooling from high temperature to low temperature. For fast cooling, crystallization is not complete. Why? Because we go very, very fast to low temperature and there is no enough time for material for crystallization. And then we coming to glass transition and everything stops. So nothing happens. Here is PET. Here we can make a simulation how the material should be produced in order to be transparent. We have cooling with different cooling rates with 10 K per minute and 1 K per minute. You see for 1 K per minute area is 38 joule per gram. For 10 K per minute is only 2 joule per gram. It's different. It's really different. Why? Because for fast cooling, there is no time for crystallization. We put this data into the software and our software can, the model, here is Nakamura model, can describe not only a shape of this material, but can describe a difference in the peak area. And now this modeling is okay, and we can see what happens during stretch blow molding. It's isothermal, about 1 hour, near, we make simulation for 1 hour, near temperatures maybe 110, 130, somewhere in this range. And we see that for low temperature, almost no any crystallization happens. Material is transparent, our bottle is transparent, and for higher temperature, somewhere here, there is crystallization and material is not transparent anymore. I will recommend you to read this ICTAC kinetic recommendation. Our software fulfill all this ICTAC recommendation. We have our website. Here we have a training section, for example, how to create temperature transition diagram, information about webinars. Here you can get a trial version for 30 days, and our software can make predictions not only for DSC, but for dilatometer, DA, acceleration, reaction calorimetry as well. Now, just one click for software. I would like to show you how it works. Here we have some data for epoxy, and you see one peak, main peak is exothermal, and here is endothermal peak. And now we can add firstly a step for main peak and make optimization of it. Yeah, here something like this. Now we have very good, really perfect fitting for main peak, but here is nothing because we have still one step reaction. We can add additional step here. Simulated curves have two peaks. We can move a first peak to the left and maybe remove, maybe exchange its direction. Now we have this position for the first peak and make optimization again and see what happens. Now the software make optimization for the whole model for all reaction steps, and as a result we have R square is 0.9993, and here a really good fit between experimental data you see and our simulated data. And now we can make predictions. You see isothermal, dynamic, we can make switch on temperature. Here is multi-step. You can put, here we have 2 steps, small, fast heating, slow heating, then adiabatic, climatic, and all other things. Thank you. Questions?
Yeah, perfect. Thank you, Elena, for this great presentation. I can see we have again many questions as today in the early morning. I would say I would pick out one or two questions, and then the other questions we will answer via email. So the first question is it possible to upload other data into the software?
So if you mean other data, the data from other manufacturer,
Yes, I think it's the right one. Yeah.
Yes, yes, we can load data from other manufacturer, so it should be ASCII data with 3 columns: time, temperature, and signal. Signal could be either DSC or TG or something else, and then it's possible to load it and analyze it, and we have a lot of experience with this.
Okay, perfect. And then the second question, are there preferred heating and cooling rates, particular for curing and crystallization kinetics?
So for curing, we usually prefer heating and isothermal. It depends on your target. So if your target is usually isothermal, then the isothermal data must be in initial data set. So usually we have heating and isothermal for curing, and for crystallization, again, it depends on your target. If your target is only isothermal predictions, then it's enough to have only isothermal data for modeling. But if your target is predictions for a range near glass transition, or if your target is predictions what happens during cooling or some complex temperature program, then in this case it is necessary to have cooling in any case and probably isothermal together. And then you can put all data together, isothermal and cooling, and create one model for all data. Thank you.
Okay, thank you very much. I think we can come to an end now, if it's okay for you. The other lots of questions, as I already said before, we will answer with our email. And then I would say, Elena, thank you for your great presentation, and thank you for your participation all around the world. And yeah, bye-bye and have a nice day.
So thank you for everybody of you for your time and for your attention. And in any case, I will send emails and answers for each question. Thank you very much. Bye.